Welcome back. So although most of this part of the lecture is going to be about exponential growth and decay, we're actually going to start by talking a little bit about linear growth, because I think it's quite important to see the differences between the two and the kinds of things that we might model with linear versus the kinds of things we might model with exponential growth. So linear functions are really good for modeling systems that are additive. What do I mean? Well, suppose we want to model the cost of buying X packets of instant noodles, and you happen to know that instant noodles will cost €2 per packet. Well, let's think about what your cost is going to be. Well, if you don't buy any packets of noodles, your cost is going to be 0. If you buy 1 packet, then your cost is going to be 2. Buy 2 packets, your cost is going to be 4. By 3 packets, your cost is going to be 6, 4 packets, 8, and so on. And my claim is that this is additive. And what I mean is that every time you increase the number of packets that you buy by 1, you're going to increase your cost by 2. So whether I go from 0 to 1 packet, all that's going to happen is that I increase my cost by 2. If I go from 3 to 4, I'm still only increasing my cost by 2. So each time I'm adding 2 to my cost. So it's an additive model. An increase in, if you like, our independent variable, the number that we buy, results in an additive increase in our dependent variable. Another example that you've probably seen quite a lot in physics is if we're looking at the distance that's traveled over time if you're going at a constant velocity. So let's imagine that we're traveling in a straight line and we're going to go at 60 kilometers an hour. How far do we travel? Well, if we haven't traveled anywhere, we haven't done anything. But if we travel for 1 minute, then we will travel 1 kilometer. If we travel for 2 minutes, then we'll travel another kilometer. And so on and on. So it will end up having a nice straight line over here, which basically says every time that we increase the amount of time we've traveled by 1 minute, we add on 1 kilometer to the amount that we've traveled so far. So it's additive. Now those are kind of two silly dinky examples, but these are actually useful out in the real world. For example, if you want to model the height of a child between 17 and 31 months, this is what the data says, and you can see that you could probably fit a very nice straight line through there. So this would tell you that no matter whether you look between 17 to 19 months or 25 to 27, over that period of 2 months, the child is going to grow the same amount, which looks like it's about 1 centimeter or so in 2 months, maybe a little bit more. So linear models are good for things where every time your independent variable increases by a certain amount, your dependent variable will just add on a certain amount or subtract if you're going negative. So it's an additive system. But obviously there are plenty of things that we'd like to model that don't actually look like that. So here we have a very nice GIF of some bacteria who are growing at a furious rate. We start out with 2, then 4, then 2, then 4, then 8, then 16, and suddenly they're just like all over the place. And that definitely doesn't look linear. Similarly, we might think about the amount of radioactive material. If we start out with 100 nanograms of carbon-14, which is a radioactive isotope that gets used for dating things. If you start out with 100, if you look after 2,000 years, you'll only have 78.5 nanograms left. After 10,000 years, you've only got 29.8. After 20,000 years, you've only got about 9 nanograms left. And plotting that, you can see that that's not a linear function. So there's something else going on here. Another key example that gets trotted out a lot for things that are not linear is good old human population and how it's changed. So you might, if you were looking at this, say between 1 AD and 1200, you might think that looks linear. But certainly by the time you get to the 1700s and looking beyond there, if you look at how our population has changed, that's definitely not linear. So we need some other kind of model in order to determine how these things change. And that's what we're going to have a look at. So the key thing to think about in each of the cases that we've looked at, the bacteria and the decaying and the human population, is the amount by which the quantity changes over a given time period depends very much how much of the quantity you have at the start of that time period. So it's not like a linear change where it doesn't matter whether you're looking at time t equals 0 or time t equals 600, you will still have the same change between if you carry one time step. For this kind of growth, multiplicative growth, which is also called exponential growth, how much you start with is going to really depend one time step later how much you have. So the amount of change is a multiple of the current value. So if you start out with very little, then you'll end up with just a little bit more and a little bit more. But if you start out with a huge amount, and then you multiply that, you're going to get another huge amount. So you get big changes happening. Let's model this a little bit. So let's suppose that we're starting out with 3 bacteria, and we have a particular kind of bacterium that divides into 2 every hour. Okay, so at t equals 0, we have our 3. At t equals 1, each of those 3 has split into 2, so we've got 3 times 2 bacteria, which is 6. An hour after that, now we've got 6 bacteria who've each split, and I'm going to keep using this 3 times 2. So there's our 6 bacteria. Each of those has become 2. So we multiply by 2, so that gives us 12. After 3 hours, we've got our 12 bacteria. Each one of those splits, so we get another times 2. And after 4 hours, again, there are our 24 bacteria. Each of them splits, so we end up with 48. So I've written it like this so that you can see that what's really happening over here is that we've got 3 to start off with, then we've got 3 times 2, then we've got 3 times 2 squared, then we've got 3 times 2 cubed, then we've got 3 times 2 to the 4. And just so that we can kind of see that this pattern actually fills in, remember that if we look at 3 times 2, 2 is just 2 to the 1, and we've really got 3 times 1, which is 2 to the 0. So if we look at the pattern, what we see here is that at each time step we have our initial number of bacteria, our 3 bacteria, and then it's going to, the way that that's grown is 2 raised to whatever the time is. So here in our exponent, we've got our time. So if we wanted to put this as a model, we would say, well, the number of bacteria that we have at a particular time is going to be the number we started off with times 2 raised to the power of whatever our time is. And this is our first exponential model. So if we wanted to generalize that a little bit more, so we didn't want to say that we're always starting with 3, we could generalize it and say, okay, we're just going to use p subscript 0, meaning the population at time 0, as our constant, and it's 2 raised to the t. We can even go a little bit more general than that and say, well, this 2 that we found over here was based on the fact that we were measuring that our bacteria multiplied by 2 every hour. But you can imagine a situation where they only multiplied by 2 every 2 hours or something like that, and you'd have a different number there. So that leads us to the general expression for an exponential function, which is this over here. So let's go through it quite carefully. So the first thing is, what are our variables? What are our constants? We need to make sure we get that right. So we have our y and our x are our variables, and our a and our b are our constants. What can we say about a and b? Well, the most important thing is our b has to be bigger than 0 and is not allowed to equal 1. Why do we make these crazy restrictions? Well, remember, we're raising b to some power, and we don't want to have to, for example, take -1 to the power of half to try and find the square root of -1, because we're trying to work in the real world. We don't want complex numbers. So in order to ensure that we don't end up having to do something like that, we keep b bigger than 0, because then we can always raise it to any power, positive or negative. It's not going to be a problem. We say that we don't want b equal to 1, because if b was equal to 1, then we just have, well, 1 raised to the power of anything is just 1. So actually we just have a constant function, and we're trying to get exponential growth or exponential decay. So that's just really to kind of say, well, we don't want a constant. We want some growth. As far as a goes, our a can be pretty much any real number, except we say, well, not 0, because then we just have y is equal to 0, which is a constant, and we're trying not to do that. So those are our two constants, and our two variables are x. Just a little bit of terminology. We call our b, let me use a different color. We call b the base. So in our original example over here, our 2 is the base, but you can have any number as the base so long as it's bigger than 0 and not equal to 1. And we call this x the exponent. And the key thing to notice, what makes this an exponential function, is that our exponent is a variable and our base is constant. So it might be tempting to look at something like y equals x to the b and say, maybe that's an exponential, but it's not, because here we have our base is the variable, and here our exponent is a constant. So this over here we saw in the previous lecture is a power function, not an exponential. Exponential means that your variable is in the exponent. Okay, so let's investigate these a little bit more. So using what we know now, if we start with 4 bacteria, how many will we have after 10 hours if they're going to replicate, if they double every hour? Well, we know that that's going to give us 4 for our initial and times 2 to the 10, which is a lot of bacteria. But we don't only have to, we don't only use this for exponential growth, we can use this for decay. So let's have a look at this problem. We've got a radioactive isotope and it decays to half its mass every year. If we start with 1 kilogram, how much will we have after 5 years? So when I'm working out this kind of problem, I find it helpful to just draw a little table of results so that I kind of know what's happening. So I'm thinking about what's happening at a different time and how much I've got. So at time t equals 0, I've got 1 kilogram. After 1 year, I've got my 1 kilogram and it's going to be multiplied by a half because it's decayed by a half. After 2 years, I've got however much I had at the end of the first year, and that amount, I'll only have half of it left. So if I have a look at what my exponential function is going to look like, it's going to look like, let's use n of t is going to be equal to my initial amount times 1/2 to the t. So if we just want to finish up, we want to know how much we have after 5 years. We just substitute in for t equals 5. And we've got 1 times 1/2 to the 5. And you could plug that into a calculator. So that gives you an introduction to exponential functions. And like all functions, we need to know how to sketch them. So I suggest that you do a bit of practice on that. I'm going to use GeoGebra just to show you what a few of them look like. So the first function that we're going to look at is 2 to the x. Now we've mostly been considering functions that really, they just start at t equals 0, but there's no reason why you can't have a minus in your exponent. Does this make sense if we think about what this function looks like? Well, when x is equal to 0, we've got 2 to the 0, which is 1, so that looks good. When x is equal to 2, then we've got 2 to the 2, which is 4, so that looks good. On the other hand, if we put in minus 2, we've got 2 to the minus 2, which is 1 over 4, which is a quarter. That also looks good. Okay, so this gives us a general idea of what an exponential function looks like. And you can see here that the domain is all real numbers, but the range is just positive. So how does 2 to the x compare with 3 to the x? Well, let's have a look and see. So as you might expect, when you increase the base, your exponential function climbs a lot quicker, because now, for example, when x is equal to 2, you've got, well, 2 to the x is 2 to the 2, which is 4, but 3 to the x is 3 to the 2, which is 9. So it's climbing quicker. And you can imagine that if we put in something like y is equal to 8 to the x, that's going to climb even quicker. So we've looked at bases which are bigger than 1, but remember our base can be between 0 and 1 as well. So let's have a look at those. So I'm just going to... So let's have a look at what happens when our base is 0.5. Well, now we've got quite different behavior happening. So this is where we've got exponential decay. And you can see, does this make sense? Well, when x is equal to 0, our function is equal to a half. Is that right? Oh, it's equal to 1, sorry. Of course, a half to the 0 is equal to 1. When x is equal to 2, we've got 0.5 raised to the 2, which is 0.5 times 0.5, which is a quarter. So that's right. On the other hand, when we've got, for example, minus 2, then we've got 0.5 to the minus 2, which is going to give us 4. And you can see if you change the base and make it even smaller, then you get even faster decay. So we have our comparison for our different graphs there. So spend a little time playing around with these, making sure that you feel comfortable. The important things to notice are that our exponentials are always positive. They can take any x value, but the y value is always positive. And if your base is bigger than 1, then you've got exponential growth, but if your base is between 0 and 1, then you've got decay. So I'm just going to take a quick picture of that. And pull it into our notes, and then we can carry on. So the key thing to note here, as I said, is if b is bigger than 1, then we get growth. And if b lies between 0 and 1, then we get decay. Okay. So now that we've got these functions, we need to be able to work with them. We need to know what happens when we multiply two exponential functions or divide them, stuff like that. So we have the laws of exponents, which I hope you've seen before, so I'm going to go through these quite quickly. So in these laws, we've got some constants. So a and b, please remember, are constants, and they're bigger than 0. And then we've got our variables, x and y. So one of the first things is that we can't really do anything if we have, for example, b to the x plus a to the y. We can't simplify it. If we had b to the x plus b to the x, then the best that we could do is say, well, okay, now we've got two b to the x's, so we've got 2b to the x. There's not a lot more that we can do. So adding exponentials isn't particularly interesting. But if we want to multiply two exponentials together, provided that they have the same base, we can in fact do that by adding together their exponents. So b to the x times b to the y is the same as b raised to the x plus y. Similarly, if we want to divide b to the x by b to the y, then we subtract their exponents. This is really because we have something that's not mentioned here, which is that b raised to the power minus 1 is the same as 1 over b. So what is really happening when we do b to the x over b to the y is we're saying this is the same as b to the x times b to the minus y, and then we're using our addition rule, and we're saying that that's equal to b to the x minus y. Okay. So we've looked at addition of exponentials and multiplication. Now we need to think about what happens when we take an exponential to some power. So here we've got our exponential and we're raising it to the power y. Well, then we end up multiplying the exponents. That's pretty straightforward. There is something to be a little bit wary of. Supposing we have two things multiplied together in our base and we're raising that whole thing to the power, then we can distribute our exponent across the parentheses. So let me just move my big circle there. So we've got ab, or raised to the power x, that's the same as a to the x times b to the x. But you need to be really careful. This doesn't work if you have two things added together and you're taking those to the power x. Okay, this is not the same as a to the x plus b to the x. I'm going to put a big cross through that. This is the same reasoning which says that if you have a plus b all squared, then that's equal to a plus b times a plus b, and you have to do the whole FOIL thing and have a squared plus 2ab plus b squared. It's not just equal to a squared plus b squared. Okay, so the danger here is this works when you're multiplying together inside the bracket, but it doesn't work if you're adding. So just be aware. And we've got the same idea happening here, except we're dividing. So if we've got a to the x over b to the x, then we can take out, if you like, the exponent and have a over b all to the x. So I've put together just some little practice problems. You can do those in your own time, and then I'll put the solutions in the final version of this when I put it up on Canvas. So far we've seen a couple of different bases. In our bacteria example, we used base 2, and then in our sketches we used base 3 and base 8. In real life, base 2 gets used quite a bit, so does base 10 in quite a lot of engineering applications. But there's another number that comes up a huge amount, particularly in natural modeling, things to do with population growth, things like that, and that number is e. And you might be wondering, well, what is this number e? What is it? The problem is like pi, it's irrational, so we can't write it down, so we give it a letter. It's sometimes called Euler's number. And it's around 2.7 stuff. And it just turns out that as a base for models, for exponential models, it's super useful. So where did this number come from? Well, it was discovered by Jacob Bernoulli in 1683, and he was studying compound interest. So we're going to take a brief look at how he got that. So let's take a straightforward example. So we're imagining that we've got €1, and we're going to put it in a bank account, and it's a wonderful bank account. It pays 100% interest per year. So it's got an annual interest rate of 100%. And what we want to know is what is the amount in the account and how does it vary depending on how often we compound the interest. So if we just compound once at the end of the year, then we're going to have our original €1, and we'll get that back, plus we'll get the interest, which is another €1. So remember, 100% is equal to 1. So we will get €2 at the end of the year. But now suppose instead that we compound twice. So we're going to compound after 6 months and then again after 6 months. So the first thing we need is to have our interest rate will be 50%, which is 100% over 2, because we'll split it over the 2 periods that we are finding our interest. So our interest will be 50%, which is also 0.5. So how much will we have? Well, our initial €1, after the first 6 months, we'll get that back, plus, I'm going to write this as a half, plus a half of it, so that's after the first 6 months. And then after the next 6 months, that whole amount that we've got now, we'll get that back, plus we'll get the interest on that. So what we really will get back is our original investment times 1 plus a half all squared. And if you plug that into your calculator, you'll find that that's €2.25. And this is kind of what you'd expect, because in this situation, you are starting out, after 6 months, you're getting interest, so your amount has increased, and at the end of the year, you get interest on your interest. So you would expect to have somewhat more than if you just got interest paid at the end of the year. What happens if instead we compound our interest at the end of each month? So our interest rate in this case, because we're splitting our 100% over 12 months of the year, will be 1 over 12, so 100% divided by 12. How much will we have? Well, we start out with 1. At the end of 1 month, we have our original investment plus the interest that we earn on that. At the end of the second month, we've got this full amount, and we've got to multiply that by 1 plus 1 over 12. And we'd keep doing that for each month. To find our final amount. So we'd end up with 1 times 1 plus 1 over 12 to the 12. And if you work that out, you will get 2.613 blah 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 euros. So by compounding more times, you get more interest. And if you were to do this weekly, I'm not going to write that out, you'd end up with 2.692597 euros. And the thing that you'd notice as you were doing this, if you went from weekly to daily to hourly to every minute to every second, is that it really looks like the amount that you'd be getting is approaching a particular number. And that particular number that it approaches is the number E. So as our compounding increases, our investment heads towards this mysterious number E, which is around 2.7. To see this graphically, looking at a slightly different problem, but the same basic idea. So here we're looking at an initial investment of $1,000, and we've got a 20% annual interest rate, but it doesn't matter. If we only calculate our interest annually, then that gives us the green line over here. So we start out with 1,000 for a year. We have 1,000, then we get a bit of interest. Then it sits there for a year, then we get some interest. So we get this green thing over here. So this is yearly. If, on the other hand, we look quarterly, then we get this yellowy line here. So as you would expect, we're getting more interest because we have a chance to get interest on the interest within each year. If you do monthly, which is this bit over here, again, you're getting slightly more. And it really looks like if you went to some kind of magical continuous compounding, that you'd end up with this line over here, which certainly looks like an exponential, and it turns out that it is. And it turns out that the equation of this straight line here is y is equal to our initial amount times this mysterious number e raised to our, whatever our interest rate, our 20%, to the t. So it was at looking at all of this that Bernoulli realized that this base e here is really important. It's fundamental to if you're doing something like compound interest. Now you can have a look through this if you want to. It gives a slightly different derivation of where e comes from, but it's not going to be tested. I just put it in for interest. The key thing to take out of everything that we've been saying is if you're doing compound interest and you take your compound interval and make it so small that you're compounding continuously, then you can model as an exponential with base e. And as I said, the number e is around 2.718, sometimes called Euler's number. It's got some interesting properties. So for example, if you take e to the x and take the derivative, you just end up with the same function. So we're going to see that when we do a little bit of differentiation. And similarly, if you integrate the function, then you just get the same function but with a constant. So it doesn't really change. There's what's called Euler's identity, which makes a lot of mathematicians very happy because it links together the kind of the big five numbers. So you'll notice that Euler's identity, we've got 0, which is an important number, 1, which is an important number, pi, which is a very important number, I, which is an important number, and as it turns out, e. And they all link together in this e to the I pi plus 1 equals 0. And just one kind of quirky thing, if you plot the graph of 1 over x, and then you look at the area underneath it, starting from x is equal to 1, then in order to get an area equal to 1, you have to stop at e. So the area of this space over here is 1. Strange but true. So after that little diversion, let's just summarize what all of that was leading towards, which was saying that if you invest p euros at some annual interest rate r, and you're compounding continuously, then the amount that you have in your account at a time t is given by your initial investment times e to the rt. So it's an exponential. Now, since we're mostly doing sciencey stuff and not so much with the business and the compound interest, what we'll mostly be thinking about is this function here, just e raised to the power x. And this is called the natural exponential function. It's called natural because it turns out that it crops up in so many different natural settings. When you're looking at populations, exponential decay of radioactive isotopes, things like that, it just crops up everywhere. So it's natural. So as I said, radioactive decay can be modeled as looking at the initial amount that you have times e to the minus. So this funny thing over here is a lambda, the Greek letter lambda, and it is the decay constant. So that just gives a measure of how fast this particular radioactive substance decays. Some go super fast, some not so much. More generally, if we just want a kind of really general equation for an exponential function using base e, this should look pretty much like what we had before. So things to notice here, our variables are our x and our y, and everybody else, the a and the e and the k, are all constants. So our a is telling us kind of our time, how much we have when x is equal to 0. So this is usually our initial amount. And our k is usually a kind of the rate at which we're decaying. And remember that our e is a constant. It's just a number. It's 2.7, blah, 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 blah. So if you start feeling twitchy about e, just think of it as 3. Just think of it as a number 3. It's nothing particularly special, except that it's extremely special. I mean, all numbers are special. E is also special. Okay. So we've covered a huge amount. I hope that it was comprehensible. If it's feeling new and a bit scary, then please go through the lecture a couple of times. The textbook is also pretty good, so you can work through some examples. And of course, there's the Q&A at 1:30 on Tuesday, where I'm happy to go into more detail about anything. So please spend some time working through this. We'll also spend quite a lot of time in the tutorials on both looking at the technical aspects of working with exponentials, so those exponential rules that we saw. There are plenty of examples in the tutorial, but also looking at how we can actually model stuff using exponentials. So there'll be both aspects of that in the tutorial, starting on Tuesday and also on Friday. All right, so I look forward to hopefully seeing you in the Q&A. And until then, have fun.